Um, it's not bad, especially given that it's like 70 out there. The last topic of the semester, I'm going to talk about low-level pixel access of images. You've done enough in processing now where this should make sense, and you're going to get a sense, hopefully by the end of today, you'll get a sense of kind of how things like Photoshop work. I've added a couple of links, which I should have added last time. The Nature of Code link is now here for Wednesday's class. And then the stuff I'll be talking about today, images and pixels, there's a processing page about it, which you can read about. And processing will let you load an image, as many of you have already discovered. Kendall, for example, will let you load an image. But beyond that, it will actually give you pixel by pixel access to the image to do with whatever you want. And to talk about that, I've got a simple example here. Let me just run it for you, and then I'll talk about it. So there's Eric Cartman. And that's the output of my program. If I click on this guy, here's the original version of that image, which I'm just going to kind of park over here because we're going to do various things to Mr. Cartman. So what I did was I visited every pixel and replaced it with some grayscale value. And that's the image that I get. Let's see how to make this happen. And again, I'm showing you this in case you haven't started your program yet. Another option for your program that's due now Tuesday would be to write a program that does a few various kinds of image manipulations. So maybe your program will load an image that you provide, and then it's got some instructions like hit B for black and white, hit R for reverse, hit N for negative, stuff like that. And then it's up to you to figure out how to make those things happen. And I'll show you a couple of examples today. And I don't anticipate taking the whole class period because I'm not sure my voice can handle it. But let's just see how far we get here. So processing offers something called the image object, the p-image object, processing image. So I declare this p-image object, and then down below, what I'm going to do is go out to the hard drive and grab this Cartman.jpg file, which I downloaded from the internet from some random site. I'm going to load the image and store it in this variable image. Okay. I'm going to make a canvas that is the same width as the image and the same height as the image. So image.width now is the exact width of this JPEG file. Image.height is the exact height, and I can make a canvas that's exactly the same size with this command. Then I go ahead and draw the image. Okay, and I draw the image. Probably if we could slow this thing down in time, we would actually see the color version of Cartman, maybe. And then what I do is I go ahead and load the pixels from that image, and let's talk about what happens here. So I execute this command called load pixels. And what this does is it takes whatever is currently on the screen. So when I do this image command, what's currently on the screen is Cartman's full color image. When I do load pixels, it grabs the current screen and loads it into the pixel array. Now the pixel array is somewhat annoying in the way that they decided to implement it, but in fact it's standard. It's the way that pixels are done throughout the industry, including Photoshop and other image manipulation programs. So let me draw a picture and explain to you what's going on with this pixel array. And we'll talk about how annoying that is. So here's the screen, and it has a width, and it has a height, and we know that there are these little pixels, rows of pixels all the way down the image. Okay, let's talk a little bit about what the pixel array is. So here's the first row of pixels, here's the second row of pixels, and the third row. The pixel array looks like this. And what's weird about it is the pixel array is one-dimensional. Right? And the screen is sort of naturally a two-dimensional object. How do we reconcile those two things? Well, what we do is we have this pixels. Here's the array. And what you have is the first row. Oh, first row. And then the second row. All the way down to the last row. All just lined up end to end in one massively long array. How big is the pixel array? How many elements would you expect to have in the pixel array? Width times height, right? So there are width times height elements in this array. And you might ask yourself, well, why in God's name would you do something like this? Why not just give me a two-dimensional array and let me access it the same way I access the screen? The short answer is efficiency. It turns out that two-dimensional arrays are, at a very low level, more expensive to work with than one-dimensional arrays. A two-dimensional array, and I'm not going to get into the details of it, but let's think about a two-dimensional array. When I evaluate, and you don't really think about evaluating an array element. When I evaluate this thing, there's actually a multiplication and an add in there. To figure out where this element is, behind the scenes you have j times the width. J times the width plus I. That's because secretly a two-dimensional array is also just a one-dimensional array. And the way that you figure out where the ij element is you multiply by the width, the declared width of the two-dimensional array, multiply that by j, that tells you what row you're in, and then you count over from the left-hand side I spaces, and that gets you the column. Okay? This multiplication is really expensive for a computer. And what do I mean by expensive? Well, in computer terms, expensive means that it takes a long time. So nowhere is it truer than in computer science that time equals money. And in fact, it's so true that computer scientists will often conflate the two terms. They'll say that something takes a really long time, or they'll just say that's really expensive. And those things are synonymous. This is expensive. Compare that to what happens when you plug I into, say, pixels I. Then all I do is I go forward. I jump forward I spots from the start. There's no multiplication lurking in there. So working with a one-dimensional array is less expensive than working with a two-dimensional array, which secretly has multiplication hiding in it. If you guys have done some processing now, you know that that draw function happens a lot, right? And so if you're calling this draw function over and over and over again, and you're using two-dimensional arrays, you're going to introduce some unnecessary lag. So that's the design decision. That's why we choose to represent pixels as a one-dimensional array. That said, I'm going to go ahead and violate all of that cost savings and just talk about how to treat this thing as a two-dimensional array. So let's look at which pixel coordinate ij, sorry, ij does k correspond to? Okay, so you dive into this array. You pick a k and you jump in. Which ij is that? So I pick a k somewhere between 0 and width times height, and I jump into this guy. Which coordinate, which pixel coordinate is that? This is where the percent operator becomes your friend. So here's a formula, and then we'll explain why it's true. And it's also where the division operator, the integer division operator, makes sense. So if you're given a k and you want to find the ij coordinates corresponding to that pixel, the I coordinate is k percent width, and the j coordinate is k divided by width. Let's see why that's true. Let's do it on a smaller grid. So here's a, let me add it just so that it's not sort of weirdly. So the width here is equal to 5, right? And the height is equal to 4. Okay, based on what you know, k equals what here? So it's 0, 1, 2, 3, 4, 5, 6, 7, 8, right? So that's k equals 8 in the pixel array. Let's see if this works with our formula. I equals int. Okay, what's k percent width? Remember percent? That's remainder after division by. So what's k percent width in this particular case? It's 3. And j, what is k divided by width? Integer division. 1. Good. My formulas, if they're correct, that should be the ij coordinate. Is that true? 0, 1, 2, 3. That's the I. 0, 1. That's the j. So that works. Everybody see that? Another interesting thing that you note here is height plays no role in these formulas. It's the width that matters. And that's true in any computer system that uses row major storage for its two-dimensional arrays. So I'll make a note here that this is for row major storage. You'll never ever have to deal with the other kind of storage. So it's more for just cultural reference. Row major storage, what does that mean? It means when they built the pixel array up here, they took the first row and put it in there, and then the second row, and the third row, and the fourth row. Row major storage. The other kind of storage convention is column major storage, where you take the first column, and then the second column, and the third column, and so on. If that's the kind of storage that you're dealing with, then suddenly height becomes the important thing and width becomes irrelevant. The only language I know of that does column major storage is Fortran, and I suspect that none of you in this room will ever have to program in Fortran.
I have somebody who does that.
Really? Yeah. And it's no end of confusion for people that bounce back and forth between the C-based languages like processing and Java and C++ and Fortran. I spent some time in my youth doing some mixed language programming where I would write a C program and I would get to a point where I needed to solve a linear system of equations. There's a matrix and there's a right-hand side, and I want to find the solution. And the code that I would use to solve the linear system was written in Fortran. And so I've got these arrays that are in row major storage, and then I want to jump in and use this column major subroutine in Fortran. That was fun. Why would I do such a thing? Why don't I just write my linear solver in C? And the answer is, to this day, Fortran is unbeatable in terms of speed. So to this day, there are people up at Boeing, for example, that are doing this very thing still, because the Fortran object code, the instructions to the processor, is very efficient. It's extremely efficient. And so what they'll do is they'll pull that object code in, Fortran object code, into their C programs and use that to solve linear systems. Okay, enough about that. So that's the formula for going from K to IJ. What about going from IJ, I keep doing that backwards, from IJ to K? Because sometimes it might be useful to go in the other direction. Ideas? So just one formula. So it's going to be something like K equals close. Width times J plus I. Oops. Times J plus I. J, remember, is the row that you're in, right? So to get down to the 5th row, how many rows did I have to cross over? I had to cross over 4 rows, right? So I multiply that by J, and then I tack on the I to get me in the right column. Okay. These are 2 important formulas for bouncing back and forth between 2-dimensional arrays and 1-dimensional representations of those arrays. Let's go back and look at my program now with that kind of stuff in mind. So, here's my loop that goes ahead and modifies all of the pixels. So I load the pixels from the screen. When I call this command, what happens is the pixel array is filled with pixels from the screen. This for loop, it goes from 0 and it goes up to width times height, right? That makes sense because we've already talked about the fact that this 1-dimensional array is of size width times height. So I'm going to go through that. And effectively, what I'm doing is visiting every single pixel in the screen. Let's talk a little bit about what's going on in this step. R, G, and B are going to be 3 integers between 0 and 255. And what I do is I ask, what's the red value of that pixel? So this is a built-in function. It's not one that I wrote, that takes the pixel and gives you back the red value. That's a number between 0 and 255, right? And then I ask, what's the green value and what's the blue value? And I store those guys in R, G, and B. And then I turn right around, so I get the RGB values of that pixel, and I turn right around and I set that pixel to a new color. And look at what that new color is. R plus G plus B over 3. What is that? It's the average of R, G, and B. And because this is a single value, the color constructor knows, oh, I'm just building a grayscale. So what's the biggest that this could be? 255, right? If R, G, and B are all 255, then the average is 255, and that's white. The smallest it could be is 0, and then you've got all the stuff in between. And this is precisely how a program like Photoshop will take your image and turn it into a grayscale image. So let's look at that again. So I visited every pixel and replaced it with the average of its RGB values. Chris?
That makes sense, but it seems like kind of not intuitive to me because when I see a red, it looks brighter than a blue.
It's how it's done. There are variations on this theme, but that's largely how it's done. So if you want a more sort of perceptually correct, based on human psychology and human perception, then there may be other approaches to generating that grayscale value. But this is by far the standard way of doing this. Yes. So Chris's comment is that if you're talking about grayscale, effectively what you're talking about is the relative brightness of colors. And in fact, it's true. If you look at R, G, and B at similar intensities, which is a physical quantity, and you do psychological experiments on people and you ask them which one looks the brightest, I think R wins, even though they're all at the same intensity. And that's just a construction of your neural network and your retina and all that kind of stuff. And so if you wanted to bring that information in, you could do that. It would be more complicated. All right, so there's black and white Cartman. Let's talk a little bit. Oh, and so what I do is I go through and I modify the pixels. But those modifications will not be reflected in the sketch until I call the update pixels command, which will actually redraw the screen with the new pixel colors. And in fact, I think if I comment that out, we'll just keep the old. Let me try commenting that out, and I think we'll just get stuck with the color version. Yeah. Okay? So those changes are not reflected until you call update pixels. Okay, let's do a slightly more sophisticated one. So I'm going to get rid of, I'm going to just comment this guy out. And I want to do a reflection about the vertical midline of the image. Let me show you what that looks like. Okay, so now in order to really, at least in my mind, get a grip on how to do this reflection, I'm going to go to IJ coordinates. And what I'm going to do is I'm going to visit every row. So that's the outer loop. So each time through the outer loop, we're picking a row. And I pick that row, and then what I want to do is I want to flip it over like that around the midline. A lot of different ways to do this. Here's one. So what I'm going to do is go through half of the array. So I've got myself a row. Now I've got I. What does I do? I marches across the image in that row from left to right. But I'm not going to go all the way across. I'm only going to go halfway across. And as I go across, I'm going to take the first guy and I'm going to swap it with the guy equal and opposite on the other side. I'll take the second guy and swap it with the second guy equal and opposite, and so on. All the way across, I'll do swaps. Is everybody with me? Okay. So I need a temporary place to do the swap. That's standard CS, right? If you're going to swap the values of two variables, you need a third guy to help with the swap. So I get this temporary variable, which is of type color up here. I store the current pixel value, and there's my formula, j times width plus I. That's working across a row. So I store the value of that guy, and then I overwrite it with its mirror image, which essentially is just working in from the right-hand side. And then I replace it with temp, and let's see what that does. Okay, so it's hard to remember here, but let me pull up the other guy. So there's the mirror image. It's a powerful way of thinking about images. Images as data that can be manipulated. I have time to try to maybe implement an idea from you guys. I'm not guaranteeing I can do it, but if you can think of something that you'd like to see me try, I'm willing to try it.
Can you make it like sparkle?
I think I could. Let me try that. Sparkle Cartman. Sparkle Cartman. Okay, so if I'm going to do that, I'm going to need a draw function. So let me load a draw function. So I load the image up here, I size the image. Let me do that in setup. And then let's do a draw down here. Sparkle. Okay. Mostly what I want to do at this point is check and make sure that it still works. So I'm loading the image, I'm sizing the canvas, now I'm drawing the image, loading the pixels, tweaking the pixels, and let's knock back the frame rate a little bit. And if I run this, I should really see no change. Oh, actually no. Yeah, if I run this, I should see no change. I'll get one image, yeah, and it just sits that way. I was thinking that it might bounce back and forth, but that's not really what's happening. Why? Remember what load pixels does. It doesn't load the pixels from the image, it loads the pixels from the screen. I redraw the image every time with the original image, and then I load the pixels. So I keep going back to the original image and then flipping it. I could get it to bounce back and forth, but let's stick with sparkles for now. Okay, sparkles. So I don't really want to transform Cartman too much, so I'm going to go back to this guy and get rid of this guy. And I think by way of sparkling, what I will do if random 100 less than 2 will make pixels white. Oop, wait. So I'm going to go through all of the pixels and randomly change them to white with 2% probability, and then I'm going to update the pixels. See what that does. Not quite sparkle, it's more like static. But that's a good first cut. No? I can't think of a quicker way to do it, but you see what's going on there? I'm just repeatedly going through the array and randomly setting one of them to white.
How would you make it negative?
Let's try negative, sure. So there's actually a formula for negative, and I will show you what it is. Let's see. I guess I want to go back to this one.
On the sparkle one though, could you just change the transparency of the color? Is there a way to do that?
Yeah, I could do that.
It's not like you could say like color equal probably something in color.
Yeah, you know what the problem with that is? And let me just bounce back and I'll show you and you can read about it. And if I have time, I promise to talk about it. But if you read about the image object, the p-image object here, what you're talking about is loading the pixels. Building the image with a particular format. And what we need to do is change the format to alpha. And if we change the format to alpha, then suddenly the pixel array gets a little more complicated because well, it's not more complicated. It's just that it now has 4 things in it. So actually, I guess it would be okay. I think we can do that. I take it back. So let's try that. So I'm gonna throw in alpha, and that was load image. That's p image, width, height, format. Ugh. Let me give it a pass, because the way I'm doing it is I'm setting the width and the height from the image itself, and so I don't know what the width and the height of the image actually are, and I need to use this constructor to get at the alpha guy. I bet there's a way to do it. Like I might be able to just do, well, yeah, okay. What were we trying to do though? We're gonna make it negative, yeah, okay. So the way to do negative in RGB land, you've got each of the channels, right? RGB. This is for negative. And let's say R is here. What you want to do is kind of add half of the range to each channel. So let's say I'm here, here, and here. So if I add half of the range here, I'm going to kind of land here. But what you have to worry about is what happens if I add 128 to this guy? Do you have a suggestion for how to solve that problem? You've actually seen this before. Yeah, have it loop around, right? So instead of going off the end of the range, have it land kind of somewhere in here. Right? Sort of like we did with the cellular automata. We just identify the left and the right boundaries. And the same thing here. Okay. So let's think about how that's going to work in terms of a formula. I got rid of my RGB stuff. I'm going to go back. Let me grab this guy. Call this sparkle. And what was this guy down here? This was vertical reflection. I don't know. Reflection about vertical midline. And I'm going to grab these guys and store them, and then go back to where I was. Oop, I don't want to go back that far. Let's just go there. We'll put this guy down here, just so we don't lose that. Let's get rid of this guy. Let's reformat. Okay, so there is, now we're back to getting our hands on RGB. What we'd like to do now is wrap around RGB. So we want R to equal R plus 128. But if that runs off the end, how can I fix that? Percent 256? Percent 256 guarantees me that I'm going to get a number between 0 and 255, right? Guarantees it. And in fact, this is precisely how you do the negative. Let's put G in there, and B, and then let's do a full-on color object, R, G, B, like that. And I think that'll do it for us. So I grab R, G, and B. I could have done this in one step, but I've separated them out. I grab R, G, and B. I reflect them by half of the range. And then I update the pixel. Oops, Syntax error, missing semicolon, line 19. Classy. Yes, classic. Oh, yes. Exactly. So there's the negated version of Cartman. And that's a pretty standard way of doing negatives as well, doing that exactly that formula. Any questions about that? Yeah.
So, off the top of my head, it seems like that would be the same subtracting BVR you divided by 5.
Well, you have to worry about. Actually, that might be true. I hadn't thought about that. Yeah, you're probably right. So let's try that. I'm always thinking in terms of the percent operator. Sometimes when I don't have to. So Chris's proposition is to just do this. 255 minus? That's a little different. That's a little different. What's different about that?
That's more like directly photoreactive, right?
This one flips it across the horizontal, so if it starts at 0, it goes to 255.
Yeah.
So the white became black.
Right.
And the red boost just
So the one that I did is the one that I'm familiar with for photonegatives. But this appears to be doing a similar kind of thing, and I'm not sure why the one that I used is what people consider photonegative, and what's this one, and I'm sure it has something to do with how film works and photography and all that sort of stuff, but yeah. The big takeaway here, as I've mentioned earlier, is you can do whatever you want to these things now. You can think about visiting every pixel and replacing it by an average of the pixels around it, for example. What's that going to do? It'll blur it. So you could go, you can blur things. You could pixelate things, right? Everybody's seen that where you put this sort of, they try to censor video and they put this floating pixel thing above there. How do you think that works? That's actually something that you could do here.
Just take that area and mix all the pixels.
Yeah, so take a big chunk. Let's say I'm just going to pixelate in sort of 8 by 8 pixel chunks. So I chop up my thing into 8 by 8 chunks. And I replace all the pixels in that 8 by 8 chunk by, what's a good thing to use? The average of all the pixels in the 8 by 8 chunk. And the bigger the chunk, the more obfuscated or obscure the image becomes. And that's pretty standard image processing kind of thing, and that's what's going on when you see that pixelated stuff on a censored video or something like that. They're just taking big block averages of pixels and replacing every pixel with a block average.
You can do that now when you upload a video.
Like have a blurring area or something like that. Yeah. Yeah. The idea is that it's somehow less intrusive than just putting a black box over that area. I'm not sure if that's true or not, but there you have it. Can you think of anything else you want me to do to Mr. Cartman?
You know in dream sequences when they make everything swirly? Can you do that?
I could do it. I don't think I could do it in 10 minutes though. Anything easy I could do? Oh, here's one that's interesting. That's fairly easy. going to happen?
So, block them out with just one color.
It'll be like Cartman through rose-colored glasses, in a sense. Right, so if you put a red filter over your eyes, that's what that image will look like.
Is it possible to like just change the color of the shirt?
Sure, but what you have to do is figure out what the range of pixels in the shirt is. But it's totally doable. So you could sort of do one run, like we could write a little mouse program. Let's try that. So let's just do void mouse clicked, and let's do I equals mouse X, J equals mouse Y. We do have to be careful when we do this, but okay. So I'm going to get the coordinates of the mouse. I'm going to convert that to a K. So that's J times width plus I. I'm going to go ahead and grab the RGB values for those. Can't remember if I made RGB global. Yes, I did. Good. And then I can just print out and then we can use this to kind of explore what the pixel ranges are on Cartman. So I've got to be careful here. I think I want to do load pixels here. And I don't need to do update pixels because I'm not going to change anything. So I'm just going to draw the image over and over and over again, and then explore it with the mouse. I think this will work. So this is going to load whatever's currently in the canvas, get the RGB values, and print them to the screen. Let's see what that does. So it should just be regular old Cartman sitting there. And then let's click on his shirt, and we see pretty consistent set of coordinates. We see a large red value, which is reassuring. Let's go into the yellow area. We see large red and green values. We can go to a white area. And so what you would do, Kendall, is you would just use this program to figure out what pixels are the shirt, and then you can just check. And whenever you see those pixels, change them to something else. Really, you're just limited by your imagination at this point in what you can do. It's pretty cool. Any questions about that? All right, I'm done. See you guys Monday, where we will do in-class review.